Northeast corridor.
The 10 a.m. high-speed Acela train is racing full throttle to Boston, Massachusetts. I'm used to riding freight trains back in Maine. The Acela is from a different planet.
You can feel the acceleration. It's a lot like flying. If you've ever flown in a plane and taken off, this is the feeling I'm having right now in my seat. It's crazy.
A high-speed train is defined as any train that travels over 124 miles per hour. On some stretches, the Acela Express gets up to 150 miles per hour. So it definitely qualifies as a high-speed train.
Wow, this is great. This is insane. I'm sorry. We're going 95 miles an hour right now, like within 10 seconds. It's like, boom, 95 miles an hour, 96. This is fantastic. Oh my God. 118 miles an hour. 134 miles an hour.
To keep people and vehicles out of harm's way, Amtrak minimizes crossings along the Acela route.
This is the fastest train in North America, 135 miles an hour. Geez, the kids don't even have a chance to go like this to you, do they?
The Acela shares the track with freight and other passenger trains, all of which are much slower. So dispatchers need to clear the way for this high-speed train to get to where it needs to go.
This is as tough as it gets. There's 4 to 6 tracks, trains going in either direction. Right now we're blistering a regional train right over here on this other track.
Speed limits are crucial along a high-speed line. Any collision at or above 124 miles per hour is a recipe for carnage. In September 2006, a German high-speed train hit a maintenance vehicle near Latham, Germany. The train was going at 125 miles per hour when the collision occurred. So Amtrak takes every possible safety precaution to make sure the Acela train's passengers have a safe journey.
It's impressive how fast this train goes, but what's even more impressive to me is how fast it slows down. It's not only the fastest train in the country as far as speed, but it's also the fastest braking train.
The Acela uses an electric dynamic braking system to ensure a safe, smooth, and speedy stop.
So we're in Baltimore now. Sir, we're going to stop and pick some people up and drop some people off.
When the electric brakes are activated, electricity is withdrawn from the train's traction motors, reversing their direction and slowing the train down.
They take the motor that gives you the traction to accelerate the train, and they do it in reverse.
Instead of accelerating the train with the motors, it reverses the motors.
Right.
And makes the train slow down.
But electric brakes are also energy efficient. When the traction motors are reversed, the electric power is returned through the pantograph back into the catenaries to be used by other trains.
We're taking that ability to dynamic brake, and we're putting electricity back into the overhead wire.
So you're actually taking power from the train and feeding it back into the wires?
When you're doing the dynamic braking.
And then another train will come along and use that?
Mm-hmm. It just puts it back up in there.
Now how economical and green is that? This is a green train.
But electric power is only one part of what allows this Acela to get up to 150 miles per hour. When a train goes into a curve, an inward force called centripetal force pushes towards the center of the curve and sends the train round. Just like when a biker leans inward when taking a corner. The problem for most trains is that they can't lean, so they have to slow down instead. But the Acela is no regular train. It can tilt. The train's ability to tilt around curves is the major ingredient in this high-speed cocktail.
There's the tilt. We're going around this curve. Cars behind us are tilting.
Once the train gets above 60 miles per hour, the tilt system kicks in, and the cars lean into the curve, allowing the Acela to keep going without slowing down.
Here's how it works. Each car has a tilt control center. This is where they hook the laptop up to check and calibrate the tilt of the train. you'd never notice a thing. But right now, we're stationary, you can really feel the rock.
The tilt system on the power cars gets information from a gyroscope at the front of the train. This tells each car's individual tilt mechanism what angle to tilt at. And just like on a racetrack, the train leans into the curves.
As you can see right here, there are hydraulic cylinders underneath the train that make it tilt. Because of the advanced tilt control, no one will ever spill a drink on this train. For the passengers sitting down, it's a smooth and comfortable ride.
Even though the passengers don't notice these curves, the engineer is aware of every inch of these tracks.
But you still had to slow down for this curve here. We went from
110 to 105
for this curve, but still with this train, it's only a 5-mile-an-hour difference where a regional train would have to slow down.
Getting around curves at high speed means the engineer needs to have skill and an understanding of the tilt mechanism.
He doesn't have the tilt, so he can't pull it off like we do.
Well, he's not as good as me.
You have to have nerves of steel to be in that seat right there.
We're approaching the city of brotherly love, Philadelphia, Pennsylvania.
30th Street Station.
Coming into a place like this with the electric power unit is a lot different than diesel 2 where there's no fumes.
Right.
This is another place where the electric engines really help out. And there are a lot of people here getting ready to go on this train. So from here, we're about an hour from New York?
55 minutes to an hour, yes.
Wow.
Amtrak's other major obstacle to full-on high-speed running comes from below, the rails themselves. It's hard to believe, but much of the track system on the Northeast Corridor dates back to the 1800s. And though sturdy, it's not high-speed ready.
Between Washington, D.C. and Boston, there were over 300 speed changes. It's up and down all the way.
There's one way to make this stretch ready for a high-speed train: concrete ties. In 1997, Amtrak began to replace wooden ties along the Northeast Corridor with sturdier, steel-reinforced concrete ones. Because the one hard and fast rule for high-speed routes is that sturdier tracks equal faster trains.
Every year, the railroads use up to 2 million concrete railroad ties. And this is where they're made, the Rockwell plant in Denver. Every day, 130 tons of cement, 450 tons of sand, and 600 tons of rock get delivered to this plant. This is where it starts. They dump the aggregate into the silo, it goes up that conveyor belt, you can see it going in right there, goes into the plant. This 500-foot belt takes the raw material at 90 feet to the top of that tower. The concrete is mixed in these two mixers right here. The mixed concrete is dropped into that hopper, and then it's taken over to the forms.
Each mile of rail uses 3,000 ties, each set 2 feet apart. So on one set of tracks between D.C. and Boston, there are 1.3 million rail ties.
This is where they pour the concrete. It's called the form. It's like a cake mold. The concrete goes right in there. It's got 18 of these wires, just like piano wires. They're so tight to reinforce the tie, they even grease it. The concrete goes from the hopper into the forms. Once the concrete is dry, they have to cut the ties up. 24-inch wide blades are coated in resin so